Hello, everyone. Welcome to the Active Stars session of the APO Science meeting. So just to remind you once again, each talk will be 12 minutes, followed by 3 minutes for questions and answers. And if you'd like to ask a question after a talk, please raise your hand in the Zoom, ask a question in the Zoom chat, or enter the question in the Slack channel for this session. So our first speaker in this session is Rachel Miller from the University of Colorado Boulder, and she is going to tell us about the merging of the hydrogen series in flare spectra from the dwarf M emission star YZ CMI.
Awesome.
Great, so feel free to share your screen, Rachel.
Absolutely. All right. Awesome. Does that look okay?
Yep, I see it.
Okay, great. Yeah. Can't see my notes or anything. Awesome. Great. Well, thank you very much. My name is Rachel Miller. I'm a recent graduate from the University of Colorado, and I've been working with Dr. Adam Kowalski studying the merging of the hydrogen series in flare spectra from the M-dwarf star YZ-CMI. And I'm very excited to be able to talk about it today. So, a little bit of background on what I'm going to be talking about, just some general science background on M-dwarf flares and why they're interesting, and then a little bit more about the region of the spectrum that is of interest for our study. I'm going to go through some of the details of the actual flare event that we caught at APO, and then a little data reduction details, and we'll get into some of my data. Great. So some general flare background. So flares, obviously, when magnetically active stellar atmospheres release a burst of radiation, it results in a dramatic increase in brightness for a period of usually a few minutes. And we divide these flares into two phases: initial impulsive phase, which is a sharp increase in radiation, and thus in the light curve, as you can see in this image from Kowalski et al. 2013, of a light curve tracking a similar light curve, or a similar flare event in an M-dwarf star. And then that initial impulsive phase is followed by a secondary gradual phase, which occurs over a longer time scale and appears more like a decay curve back to a quiescent state. So stellar flares are often characterized by emission in the optical and near UV part of the spectrum, which we call the white light continuum, since stellar flares can be picked up by broadband filters peaking in the U band or just bluer of the U band. And after decades of investigation and study, we still don't really understand the mechanism of this white light emission in the blue. And so examining white light emission during the impulsive and gradual phases of a flare can provide an invaluable tool to understanding the process of ionization in the chromosphere in response to impulsive heating. And specifically, we want to understand how electron density in the flare atmosphere varies across the impulsive and gradual phases. Moving on. In this image from Kowalski et al. 2013, we see a selection of impulsive spectra from similar M-dwarf flare events. And there are a couple interesting things to note about these kinds of spectra. So first thing would be the blended or broadened hydrogen lines, specifically in the region between about 3,600 angstroms to about 3,800 angstroms, which includes the Balmer lines of H7 and higher, plus calcium 2K and calcium 2H. And a possible reason for this broadening that we see in a lot of M-dwarf flares is the Stark effect. So in an environment with high density of charged particles like a plasma, electric pressure broadening can affect the spectral lines, so shifting, broadening, and blending them, overall making them harder to resolve. And this broadening of the wings of the hydrogen lines can result into them blending into a kind of pseudo continuum. So another important feature in this region, the Balmer jump or discontinuity at 3646 angstroms, the point where hydrogen is ionized from the n=2 level. So this dip is another feature that we look for. Its presence, absence, or just general weirdness going on with the dip is important for understanding atmospheric opacity, as we'll talk about in a minute. And so in this image, the blue lines are actually a Planck function fit to the data. So we do have models that can describe most of the shape of the impulsive phase spectra of M-dwarf flares as blackbody-like objects with temperatures of about T=10,000 Kelvin. And these radiative hydrodynamic models generate a geometrically thin layer in the chromosphere with a very high electron density. So we can actually directly measure that charge density, and through the amount of broadening in the Balmer line wings as they merge into a pseudo continuum can tell us about that electron density. And so in addition, when we accurately account for stark broadening and also opacity effects are included in the model of this Balmer edge region, they predict extremely broad Balmer lines and a smooth transition from that Balmer continuum into the black body continuum further into the optical region. So another important thing to note is that the 10,000 Kelvin blackbody-like radiation only lasts during the impulsive phase. So it's important to get accurately time-resolved spectra so we can not just describe but quantify how extreme the Balmer line broadening becomes across the course of the flare event. So why MDORs as flare candidates? First reason is that there are a lot of them. So they're abundant, which makes them a good candidate. And another reason is that they are very bright in the red, but they have low photospheric background levels in the blue and near UV. And so that makes them good candidates because they would have a low quiescent state where you can have high contrast of flare events coming up against that background, which makes them very visible. So this study captured the YZ-CMI flare with moderate spectral resolution and moderate exposure times with the goal of looking in detail at the white light emission, which I'll go into more in a minute. Great, so we caught a flare using the APO ARC 3.5 meter telescope, the B1200 grading of DIS. We caught a 4-minute moderately sized flare in 2017 using high cadence flare monitoring. This includes the prominent emission lines of H gamma, H delta, calcium 2H, and calcium 2K, as well as H8 and the Balmer edge region around 3646. We took 210 exposures, a variety of 30 and 90-second exposures of the object. And this is just interesting because previous studies have been done with high spectral resolution and long exposure time, such as Furmeister 2009 and Hawley and Pedersen 1991, as well as studies with low spectral resolution and short exposure times, such as Kowalski et al. 2013. This study using moderate spectral resolution and moderate exposure time is an uncommon approach to finding the kinds of features that we'll see here in a moment. Awesome. So just a little note about the data reduction. We reduced the data with IRAF in the standard way. Because we needed to calibrate so deep into the blue, we used mercury HENIAR lamps with the help of the observational specialists at APO. And here we have in this image a spectrum of a calibration lamp, the mercury HENIAR calibration lamp. And as you can see, there's quite a bit of contamination, especially along those broad wings at the base of the spectral lines, up to 60 angstroms across at some points. So this is important for us because our analysis of the pseudocontinuum relies on finding broadening. And so we want to be sure that broadening is it's tied to actual physical events and not just due to contamination in our instruments. Awesome. Moving on, yes, the blue. Okay, so here is my light curve. This, as you can see, is a light curve calculated for the prominent emission lines that I mentioned before. And we used equivalent width as a diagnostic for the relative prominence of spectral lines from spectrum to spectrum across the observation period to indicate the strength of the flare event. And as you can see here, it is very choppy. It's much choppier than that first image. There's a lot of oscillatory motion. And that could be due to a couple things. Could be due to different exposure times, maybe the contamination issue. And we will have to investigate more in depth to discover why that oscillatory motion is showing up there. But the important aspect of this is that all of these spectral lines clearly reach maximum emission in that flare event around 2.5 hours into the observation period. And luckily that choppiness won't affect our analysis later on. Okay. So here is some spectra. This is the spectra from the peak of that impulsive flare phase. So the peak of the flare and then one exposure on either end. And they are measured by equivalent width. So these are flare only or continuum subtracted counts per second. And you can note the strong response in the continuum along those notable spectral lines. Awesome. And we are going to zoom into that notable region on the left there in the blue. So we did look in detail at the region of 3650 to 3800 angstroms, where we might expect to see higher order Balmer lines and or a discontinuity or a dip in the continuum right at 3646. And as you can see here, we do see some evidence of broadening or blending in the spectrum, especially between that region, 3650 to 3800, where we don't see a whole lot of higher order hydrogen lines. And as noted before, different flares present different activity in this region of the Balmer edge feature at 3646, including, as is the case here, it not appearing at all. So what's useful here, as I talked about earlier, is measuring that wing broadening, and from that being able to determine the electron density of impulsive flare atmospheres. So by understanding that density, we can better understand this thing that we call blackbody-like, but which can't actually be a blackbody. So measuring the density will help us define the conditions in which this blackbody-like radiation is produced. And this one is just good to see the comparison of the impulsus versus the gradual phase, and they're both continuum subtracted spectra in both of these plots. But as you can see, we still have continuum response and elevated spectral lines in the continuum subtracted gradual phase spectra on the right, which then later on would slowly return back down to a quiescent state. So it is important to compare the continuum response between the impulsive and gradual phases to fully understand the heating mechanisms that operate across the course of the flare. Because the blackbody-like radiation only really matches, the model only really matches in the impulsive phase. So next steps, give me one moment. So these data do provide new constraints on the physical origin of the pseudocontinuum, or that broadening of the Balmer lines, which is included in radiative transfer models as a sort of dissolved level continuum opacity. And future work will have to be done looking deeper into the blue near UV optical part of the spectrum with higher instrumental resolution and time resolution. And valuable work is still yet to be done in the blue. So we can figure out a lot about the nature of stellar flares by investigating the Balmer continuum. And I am ready for questions.
Great. Thank you very much, Rachel. So if there are any questions, feel free to raise your hand, put them in the chat, or enter them in the Slack channel for this. So John Wisniewski, go ahead, ask your question.
Sure, thanks. Rachel, when you had your plot of equivalent widths versus time, was that continuum subtracted or not?
Equivalent width versus time, that was not continuum subtracted, just because we were looking for the location of the flare within the data set. And so that was more of a, I can go back to it if you'd like. That was more of trying to track down which flare spectra contained that, that information that we could then continuum subtract.
Gotcha, thanks.
Of course.
So Russet, please ask your question.
Yeah, so it was unfortunate that that you did see this flare at a time when this had a lot more scattered light, and I was wondering if you'd had any luck in the past year when the scattered light has been lower on the blue side.
Yeah, so I didn't participate in the gathering of this data. So this is my one, the observation made on November 26, 2017 was the one data set that I've been working with. I think if we were going to look further into this, if the contamination issue has been more resolved in recent times, then I think Dr. Adam Kowalski would probably have more knowledge about that and be better able to answer that question.
Thanks.
Thank you.
Great. Well, I can ask one question. So, Rachel, is it more important to get more data for this star or to do one of another stars that might be acting in a similar way that's also observable from APO?
Yeah, so what's great about this type of flare is that it is pretty common across a lot of target objects that we can observe pretty easily. YZC-MI has been looked into in the past. It's a pretty popular flare candidate, and so I think it is a good target if we're going to look into this further with that higher instrumental resolution and a time resolution. Yeah, I think it is just a matter of sort of narrowing in on this region and really getting good exposures of it, so we can examine, actually measure that broadening. So I think it is as good a target as any, if that makes sense.
Great, thank you very much. Let's all thank Rachel once again.
Thank you so much. Stop my share.